Welcome and good afternoon. My name is Dwayne Brown with the Office of Communications here in Washington, D.C. On November 4th, NASA's EPOXI mission spacecraft conducted a successful flyby of Comet Hartley 2. The spacecraft images were seen all over the world, and the mission is providing scientists the most extensive observations of a comet in history. Well, today is part 2, the science. You'll hear brief presentations, then we will open it up for questions. Let me introduce you to today's presenters. First up will be Michael Ahern, EPOXI Principal Investigator, University of Maryland, College Park. Pete Schultz, EPOXI Scientist, Brown University. Tim Lawson, EPOXI Project Manager in the Jet Propulsion Laboratory in Pasadena, California. And Jessica Sunshine, EPOXI Deputy Principal Investigator, also from the University of Maryland. But before we get started, it's my pleasure to invite to the podium Dr. Jim Green. He is the director of NASA's Planetary Science Division, and he has an incredible amount of planetary launches, missions, such as EPOXI and other activities that are on the horizon. He's going to set the stage, put things in context. So ladies and gentlemen, welcome Jim Green.
Well, it's really a great pleasure at this time to be able to talk about some of the scientific results from a fabulous mission. But before we do that, I thought I'd give you a little background. In January 2005, the Deep Impact mission was launched. And by July of that year, its impactor hit a comet, Tempel 1, and evacuated the top layer surface. And that mission was designed to be able to look at the below surface composition and was a tremendous success. Upon the completion of that encounter, the spacecraft was in excellent health, it had plenty of fuel, and a new mission was devised and approved by NASA headquarters. And that mission was named EPOXI. Now, the reuse of this particular spacecraft at a fraction of the cost that it would take to build a new one is just a tremendous bargain for NASA, the science team, and the nation. And as Dwayne mentioned, on November 4th, just 2 weeks ago, EPOXI flew by another beautiful comet, Hartley 2. And by the end of the day, a press conference was held and talked about those initial results. However, it's only been over the last 2 weeks when the science team has actually had the detailed opportunity to sit down and look at the observations and come to some consensus and dig into the data that we're here to hear about today. There's some tremendous results that they're going to present, some astounding images that we will see. And without further ado, let me turn it over to Michael.
Thanks, Jim. Today we're going to talk about the ice that is spewing out of Comet Hartley 2. When we excavated 10,000 tons of material from Comet Tempel 1 5 years ago, we looked really hard for the chunks of ice that we thought we would be excavating, and we didn't find any big chunks of ice. Most of the water came out as ice, but it was all in tiny micron-sized grains. So when we saw the images come down, even in real time in the raw data, and realized we had a cloud of snow around the nucleus, we were astounded because it was so different from Comet Tempel 1. And it's driven by a large excess of dry ice in at least one end of Comet Hartley 2 and possibly in the other end as well. The first image shows an example, and many people will know that our high-resolution instrument is slightly out of focus, so we have to process the image in order to resolve the details that should be there, and that's in the next image. And here you see a lot of things. You see lots of detail on the nucleus. We can trace individual jets down to discrete features on the surface of the comet. But and we can also see that there are jets clearly coming from features on the night side of the comet in darkness. And that's an important result, but today we're not going to focus on the nucleus. We're going to focus on that swarm of points around the nucleus. Those are not stars. Those are all chunks of ice. And to focus on those, the next slide is just off the edge of the nucleus. Again, this is the image before we manually process it to fix the focus. In geek speak, it's a scene-dependent iterative deconvolution, but basically we just process the image to fix the fact that it's out of focus. And the next image is in focus. Every one of those pinpoints is a chunk of ice. It's just a point of light to us, so we can't measure the sizes directly, but indirectly, just from the brightness, we think the biggest ones are at least the size of a golf ball and possibly up to the size of a basketball. They'll probably be very porous. And for the details of where they are and how they're moving around, I'll hand over to Pete Schultz.
Thanks, Mike. I mean, when I see that image, it just looks like a snowstorm, and that's what I want to tell you about. I want to find out I want to show you how we found out what these were, how these were, we detected they were snowballs, where they are, and we wanted to find out what they mean. So if I can have that first closer look, this shows a close-up look where you see on the left-hand side is that blurry image from the defocused instrument of the high-resolution imager. On the right, it's in focus now through that deconvolution, and I've identified some of the streaks. The bright ones are identified in red, the faint ones are identified in blue, and then the small specks that you see are circled in yellow. So there's an assortment of different things we see when we look at very high resolution. And what these are really indicating, these streaks are telling us that in fact it's related not to their motion, but the motion of the spacecraft. We're going 27,000 miles per hour, and as we're whizzing by this nucleus, we're seeing these features. The longer the streak, probably the closer it is to the spacecraft. The fainter it is, probably the farther away. So we're already getting a sense that we're seeing a lot of material in the field of view. So let's take a different view, and this is now the medium resolution imager. And on the left, you'll see this context view. And that's kind of important because you see this long shadow cast by the nucleus on the inner coma. And that's dust because you can't cast a shadow in space. It does cast it on the dust. But if you look at the right, you'll notice that there are, again, all these specks. And this is in the medium resolution imager. So the question is, which ones are actually stars, which ones are dust, and which one are artifacts? And so to do that, we need to take one more step. And so in the next time step, I'll show you a flicker movie. And this flicker movie allows you to see things in motion. And when we first saw this, our mouths just dropped. Our whole team just dropped. Because we can begin to see, if you look very close to the nucleus, you can see things that are slowly moving, but then as you go farther away, they're really migrating. This is telling us that there's depth. And so we are seeing now, with this imaging, we are now seeing two different instruments, the high resolution and the medium resolution. We're seeing them with two different instruments, and we're seeing the same objects. To me, this whole thing looks like a snow globe that you're just simply shaking and watching it fly. So now the question is, where are they in space? And to see that, we've got to go to this next time step, where here we actually track out particles. And so you notice that red one just zipping by. And this is kind of like being in a car and with the signs just flying right by you, with the other ones in the distance, like the trees in the distance, staying pretty steady. So this gives you a sense that we are seeing things from different distances away. And the importance of this is that we can actually locate these objects, and we might be able to tell where they are with respect to the nucleus in space. Now, we now know that these particles, as they're moving, are still going less than about a meter per second. So they're not going very fast. Again, it's really the spacecraft doing the moving for us. So with that, it also tells us that we're seeing displacements. And when you see displacements, you can see things in stereo. So if you will, please put on your stereo glasses and we'll take a look. We'll go down into 3D. I love this look. Now, be sure, first of all, that the blue filter is on your right and the red is on the left. And I also suggest that if you're looking at this on TV, move back to the monitor, because I think that'll help you see this better. Notice that this is a slightly different orientation. We have to do this because the stereo is constructed by the motion of the spacecraft. And now the sun is really at the top. Now, I've circled some of the particles, and as you look at these particles, even without stereo glasses, you can see the depth. Some of the ones that are near the nucleus are pretty far back, or actually kind of sticking out in front. And then over to the left, you'll see some that are staying way in the back. And for those of you who don't have stereo glasses on, you can do this later, but you can see that there are some of these specks, the green and red are far apart. Those are the ones that are close to us, and those that are not far apart are the ones behind. So we can still clearly see in this case, just like with the streaks, that there's some way in the foreground, some way in the foreground. So these objects are really surrounding the nucleus, and now we have kind of this estimate of size, which Mike suggested somewhere between a couple of inches to as large as a couple of feet. But we have the distribution as well. The team members have estimated that for every 10-inch particle you might see, there'd be 1,000 of the 1-inch particle. So there's a whole range. So when I look at this image, especially in 3D, this whole thing kind of appears to me as if this nucleus has a posse of many comets surrounding it. So Jessica will describe how these things are lifted off the surface when she talks about the process. But now let me pose a different question, which is, could any of these actually hit the spacecraft? So if we go to the next time step, here's an image of us approaching. Now, as you see those two streaks that are circled, realize that those are 3 times closer to the spacecraft than they are to the nucleus. And you also realize we're heading toward the comet, at least offset from the comet. And that raises the question, did we get hit? Should we be concerned? And so with that, I'll turn it over to Tim.
Thanks, Pete. So talking about flying through this field of ice chunks and snowballs and other hazardous objects for the spacecraft, first I want to remind you what our flyby geometry was. If you roll the animation, it'll show you a rendering of what the flyby looked like as the spacecraft approached a comet and went by it, and then it'll be followed right after that by the view of the comet that we had from the spacecraft imagers. And just reminding everyone, we flew by the comet at a distance of about 435 miles. We flew by it at a speed of about 27,000 miles per hour, and the spacecraft was slightly below the comet in the sunplane, and that produced the views that you'll see here. So as we look back and try to figure out whether or not the spacecraft was damaged at all or whether we were hit by any of these particles, first order look, you can look at the health data and all the telemetry from the spacecraft to tell whether everything is still working fine after the flyby. And that data we got down very shortly after the flyby. The first set of data we brought back were telemetry files before we started bringing pictures down. And so we were able to tell right away that we went past the comet through the coma without any kind of discernible damage to the spacecraft. All the instruments and all the equipment on board the spacecraft was working just fine. So then the next step is to try to figure out whether or not we might have gotten hit by any small particles that we could detect. And so to talk about that, I'd like to refer to this model of the spacecraft. If you look at this model here, if you imagine being hit in a part of the spacecraft that's away from the center of mass, you can imagine that imparting a little bit of torque to the spacecraft and moving it. And so those are the kind of clues that we'd be looking for. And so the team undertook a pretty detailed examination of the attitude data on the spacecraft. We have 2 different ways of sensing the attitude of the spacecraft and looking at both sets of data, trying to pick out, get rid of the noise and look at real attitude excursions. That gives us an idea of where the spacecraft might have moved as we went through the flyby sequence. Then you have to take and rule out any movements that are due to things going on the spacecraft. For example, receiving position updates from the AutoNav software, filter wheel movements can be sensed in the attitude data, and even the IR scans as the spacecraft would move back and forth to perform the IR scans. All of those things you have to rule out because that obviously then would not be a dust hit. So after doing that and going through a fair amount of detailed analysis, we've identified 9 events in the 10 minutes around closest approach that could possibly have been dust hits. Once you identify those, then you have to try to bound, well, what size particle was it that might have hit us? And so for that, you have to make some kind of assumption. The assumption that we used in this analysis was basically assuming something that hit the spacecraft about 1 meter away from the center of mass to try to bound the size of the particles. Based on that, we estimate that these 9 events, the particles that hit us, looking at the attitude excursions that we saw, ranged from about 0.02 to 0.2 milligrams in weight. 0.2 milligrams, that's about the weight of an eyelash. So you can imagine something that small, that light hitting you and causing an attitude disturbance. Well, traveling at those kind of velocities, you can impart a fair amount of energy when you hit an object with that. So that's based on our analysis and the telemetry we have from the spacecraft. We can conclude that, yes, we may have been hit by some of these small particles, but none of them were large enough to cause any damage to the spacecraft. That's an important point here. I'd also like to emphasize the point that November 4th wasn't the end of the story for this flyby. We're still continuing to collect data. We've collected about 32,000 images of the comet since November 4th. We continue to look at it about every 2 minutes and acquire data, returning over 3,000 images a day of data. By the time we're all finished with this science mission, around Thanksgiving is our last imaging session, we will return about 120,000 images of the comet, and that represents about 22 gigabytes of data. So this undoubtedly gives us an exhaustive view of this comet, more than we've ever been able to return before from any other comet. And so after that, we'll do a final calibration of the instruments, and the spacecraft will be in a fairly quiet mode in December, awaiting further instructions. So to talk a little bit more about all these chunks and different things that we might or might not have been hit with, Jessica Sunshine is going to tell us about the composition.
Thanks, Tim. So what I'd like to do first is explain how is it that we know these snowballs or snowflakes are actually made of ice. And second of all, show you that while they appear to be quite large in the context of the imagers, they're actually quite small. So with that, let me start with explaining that in the same way that we can use a prism to break light into colors of the rainbow, our high-resolution instrument includes an IR spectrometer that actually uses a double prism and allows us to measure materials in the infrared, which is redder than we can see, but is a domain in which we can identify some very important materials as well as map them. So if I could have the first slide, please. So here in white is a measurement of the coma, or the atmosphere, of Comet Hartley 2 taken just off the nucleus on the CO2-rich end. And you can see in this image that the gases appear as positive features, that is peaks. Water vapor is denoted in blue. We have a very strong carbon dioxide signature in green, and a weak but important signature due to the vaporized hydrocarbons in red. But for the purposes of this conversation, we're really interested in the ice. And the ice is actually things that appear negative in this measurement. And if I could have the next slide, I'll emphasize that a little bit. Same measurement of Hartley 2, but now you see that there are three regions denoted by the blue boxes where light is absorbed. And these three signatures I'm comparing in purple to laboratory measurements of ices at different size crystals. And you can see there's a one-to-one correspondence, and that this, in fact, is how we identify the presence of water ice. What's also interesting here is that if you look at the different sizes, now these are all very small, 1 micron up to 100 microns, you can see that the 3 micron band, that's the area with the largest box, actually starts to disappear. And by 100 microns, it's gone. And yet, if you look at Hartley 2, it has a very strong 3 micron absorption. In fact, it's about 50% of the light that hits the ice grains are absorbed. And because of the strength of that band, the depth of that band, we know that the ice on a fundamental level can't be bigger than 1 or maybe somewhere between 1 and 10 microns in size. And so that's about the thickness of our hair. These are very fine particles. So what that means is that the snowballs are not what we might have thought to begin with. We're not seeing hail-sized particles, softballs, or even ice cubes. What we're seeing are fluffy aggregates of very small pieces of ice. And so they're akin more to maybe a dandelion puff that is very hot, empty air that can easily be broken apart than an ice cube. And that might explain why we didn't see any hits on the spacecraft, among other reasons. So let me move on to show you the distribution of these materials around the comet. If I could have the next slide. Okay, on your left is an image from the medium resolution imager like Pete showed, but this time it's enhanced to show the material jetting off the nucleus that is in the coma. And you can see there's a very strong jet on the sunward side on the right, and some weaker jets on the anti-sunward side where we were showing before in the dark. On your right, in green, is a map of the relative abundance of carbon dioxide, or CO2, that is vapor that's come off dry ice. And you can see it's very enhanced in the same places as the MRI image. That is, the jets that we're seeing are actually composed of carbon dioxide. So you can see a strong signature off the sunward end, weaker signatures off the anti-sunward end, but nothing in the middle. In the next slide, you'll see the dust that Pete was talking about. Here, the nucleus itself is white, but if you look at the red parts, you can see the dust coming off. And there's a very good correlation between where the dust is, these bulk solids, and the carbon dioxide is. And in the next slide, I'm going to show you the ice here in blue. And again, the areas that are white in this area that are the most intense are the areas where we map water ice. And you can see it one more time along the sunward side. And if I could go back one, please. Thanks. The sunward side, and in the underneath side in the dark on the upward side. And so what we're seeing here is this story that we've noticed when we started getting data from this comet, that it is the CO2 that is driving the materials, the dust and the ice. So ice grains and dust are being pulled from the inside of the comet with the carbon dioxide as it sublimes and heats up. So when we looked at this, we thought, all right, well, we might as well look at water, but it should be pretty straightforward. You're going to see water evaporating and subliming where the ice is. Well, that turned out to be really not the story at all. And to our great surprise, if I may have the last slide, if you see the distribution of water vapor, while it's true that water is where the ice is, in fact, it's everywhere, particularly on the sunward side of the image, there's a tremendous enhancement of water vapor coming out of the waste of this body. We wouldn't expect this at all. And so what we're seeing is an indication that here the ice is still on the inside. It's being heated up by the sun, and that drives the water off. And so this comet is doing two things at once. On its ends, the CO2 is evaporating and dragging the ice grains with it, and that produces water in the coma, in the atmosphere, while in the middle, the smooth dust-ridden region of the center of this comet, we're seeing subsurface ice evaporating. And I'm going to turn it over to Mike, who's going to explain that this subsurface ice is something we're very familiar with.
Thanks, Jess. The next picture shows the two comets that the Deep Impact Flyby spacecraft has visited. On the left, Tempel 1, and on the right, Hartley 2. Obviously, they're very different sizes. But there's one other very obvious difference. We know there are jets surrounding Comet Tempel 1, but you can't see them in this picture because they're too faint, whereas the jets coming off the end of Hartley 2 are really obvious. And they're really obvious because those jets are filled with ice crystals. And ice, as you know, or snow, reflects light very efficiently. The next slide gives us an indication of how the sublimation works. On Tempel 1, there's ice somewhere between a few inches and a couple of feet under the surface. We know that because we excavated it and we saw it in Tempel 1. And the ice gets warmed by the sun's heat percolating down through the thin layer of dust and evaporating and coming up through the porous material on top. And on Comet Hartley 2, we have this accurate scale model. Got a nice smooth waist, rough ends, an excess of dry ice on the inside, and in the smooth waist, lots of water ice, frost. I wasn't able to get the dust layer on top, but we have water ice coming out of here, and we have dry ice subliming and dragging water ice out the ends as the comet turns around. I wasn't allowed to put water ice in with the dry ice because of fear of taking out one of Pete's eyes.
Thanks.
But this is basically our idea of what's going on. So the waste behaves like Comet Tempel 1, and the next slide shows more what's happening with Comet Hartley 2. There are real jets coming out of identifiable features on the surface. They're dragging out ice crystals with them. The ice crystals are later evaporating. Those huge snowflakes are producing more than half the water that comes out of Hartley 2. But it comes out as a very diffuse cloud. So the water you see coming from the nucleus, you see only from the waste here. So what does all this mean? Why do we care that they work differently? They work differently because they have different composition inside. Comet Hartley 2 probably has more dry ice than any of the other comets for which carbon dioxide has been measured, which is only a dozen or so, actually fewer than a dozen. Does that say that these comets formed further from the sun than did Tempel 1? So there would be more dry ice relative to water ice could form? That's the next step that we have to take in understanding that, and the last picture shows you, reminds you what we're talking about. I'll leave that up while I wrap up. We really want to understand how things got mixed up in the early solar system when the planets were being made. We would really like to know, is the CO2 at this end the same concentration as it is at the other end? That's going to take a lot more analysis of our data, but we should be able to get that out by looking at the jets when opposite ends are facing at the sun. Pete is now the sun. And
Thanks, Mike.
we have much more work to do in this area. And ultimately, we want to use this to constrain how the planets formed, in other words, how we got here. And with that, I'll leave it and we can take questions.
Before we take questions, I think it's certainly appropriate. I want to say congratulations to you all. And for folks here in the studio audience, please give these folks and the entire team, there are a lot of folks involved in this, a round of applause for the work that they've done. With that, we're going to open the phone lines, and for the media, we have a number of folks on the line. We'll see if we can just start with one question and a follow-up, and if we have time, certainly we can come back. And if you can address your question to a particular individual on the panel, that would be helpful. So we will turn it over to the phone line. First call is from Emily from the Planetary Society.
Hi, can you hear me?
Yes.
Okay. I've gotten a lot of reader questions that are confused about how we can see the jets being lit up at the surface. And I know that there's things like forward scattering going on, but I'm wondering if you can just explain that in terms that the public can understand. How do we...
Okay.
You cut off a little bit, but did you get those question, Mike?
Yeah, this is Mike Ahern. I'll take that question. I think I understood it before you got cut off. The gases that come out you don't generally see when we take pictures because most of the pictures we take are white light. Sometimes we take pictures in the that are sensitive only to the gas of a particular molecule, but usually they're white light. And we see the jets because sunlight is reflecting off the tiny particles of dust and ice that are being carried up by the jet of gas. If a jet is being produced on the dark side, we in fact don't quite see the base of the jet. We only see the jet when it gets up above the edge of the nucleus so that the sun is above the horizon.
Next question is from Kelly from Sky and Telescope.
Yeah, thanks. Thanks very much. This is for Jessica, I think. Comet Halley, when was visited back in the 1980s, its particles were largely dominated by organic material, I think, and I'm wondering if you're seeing anything comparable, or is this really a comet of a very different composition?
Well, the organics are a little harder for us to get at. I think I showed some evidence that we're seeing sort of a bulk organic peak at this point, and we've, quite frankly, not had enough time to look at it to really tell you too much about its organics. So I hate to not answer the question, but we really don't know yet. And I have to confess I don't know as much about Halley as certainly Mike does. Is there something more obvious there?
No, it's clear that we have organics.
Right.
It'll take a lot of work to estimate either what kind of organics they are or how many molecules we're getting, whether they're very abundant compared to the water ice grains or compared to the dust grains that are also there, the refractory dust.
Next call is from Mike Wall from Space.com. Go ahead, Mike.
Oh, yeah, hi. This question's probably for Tim, I guess. Yeah, like I just wonder. I mean, yeah, you actually talked about it just a little bit, but do you know any more about the ultimate fate of the spacecraft? Like, what's actually going to happen to it now, or is that still being decided?
Mike, we're going to get Jim Green a microphone, and he will be the appropriate person that can answer that.
Yes, this is Jim Green. We have went out to the community with a request for information and interest in potentially a follow-on activity with this particular spacecraft. And that has closed. We've received that input, and we're currently in the process of reviewing that material. So no announcement is to be made at this point. It's just too early.
We have one question that I have here from one of the .coms, and actually they want to hear from each one of you on your personal thoughts with the data that you have thus far. How has it personally changed from what you have done in the past to now and what you hope to probably do in the future? So that's a personal thoughts on what you've really discovered at this point. So we'll start with you, Mike.
Well, we'll go down the table in order, perhaps. For me, it has emphasized how different comets are from one another and how understanding them is a much more complex problem than the rather simplistic approach I like to normally take. And clearly, when you want to understand how things happen, you want the simple overview, but you have to understand the details as well, and things have just gotten much more complex.
Yeah, I guess for me, and some of the listeners will understand this, but I was an amateur astronomer as a kid. And so I saw two comets, Comet Mercos and Comet Aaron Rowland. And, who would have thought that we actually get to see a comet close up like we just did? So that's one thing that just looking back in terms of my personal feeling, it was really sort of very internal. In terms of where we're going, I'm really, really curious about where these particles are, how big they are, where they're going. I'm hoping we can actually determine something more about the particles, and I'll be a happy camper then.
From an engineer's viewpoint, I've been working on small bodies missions for about the last 6 years, starting with the first Deep Impact mission and then working on Dawn, and then back to this mission. And getting to these small bodies and getting to comets is hugely exciting and satisfying for me. And then just on top of that, the incredible data that we're finding when we fly by these and get up close and are able to really start understanding what these are like, and just understanding that, so far anyway, we've never been to any two comets that are the same. Every time we have new surprises, amazing new things that we find. Those kinds of things I find just very exciting as an engineer to be able to participate in those. And so I look forward to future missions to these kinds of bodies.
Well, I think for me, it's the wonderful chance to see Hartley 2. And, I used to have a favorite comet. It was called Temple 1. And we have a new favorite comet, Hartley 2. And, well, like a good parent, they both have their strengths and weaknesses. And it's an incredible opportunity to be able to take the same exact instruments, especially the spectrometer, and compare one for one place to the other. And my personal interest lies in the geology and trying to understand the features that we see both in quite detail on Temple 1, and now with Hartley 2, the amazing difference is that we have the jets there. And so we can ask the question, what of these features are caused by the jets, or which is cause, which is effect? And comparing the two surfaces, I think, is really going to let us understand how these work. And as far as the future, I love flybys. And Jim, this has been a wonderful experience. I wouldn't do it any other way, but I sure as heck like to get a little closer to these guys and actually land on one of these. So, and that's going to happen soon with Rosette.
I'd rather hit one.
Well, that too. We can do both, Pete. We'll talk offline, right?
Okay.
Okay, thank you all. Let's go back to the phone to Kelly Beatty, again from Sky and Telescope. Go ahead, Kelly.
Thanks very much. I guess I want to try this spectra question from a different angle. Mike and Jessica, can you give us a sense of what kinds of other observations were done at the same time during this flyby that might help you constrain the spectroscopic nature of what's coming off the comet, Spitzer, ground-based observatories, and so forth?
This is Mike Kelly. There were a lot of ground-based observations. For example, both Keck telescopes were being used, and they were being used with high-resolution spectrographs. IRTF was being used. And all these instruments have much higher spectral resolution, so they can more easily separate out the different kinds of organics that are present. Our spectrometer, where we're trying to cover 1 to 5 microns all at once, you can't get high resolution everywhere on a finite number of pixels. So I think the key to unraveling it will be the observations from a wide variety of telescopes like the 2KEX and the IRTF, but also including the European facilities and various telescopes in space. Space Telescope was making UV measurements to measure carbon monoxide, for example, and the VLT was being used, and I don't know the details of all the other ones. We have measurements from the Odin satellite of water vapor. I can't give you a complete list.
Jessica, did you want to add something?
No, Mike knows more than I do for sure on that topic. So
Okay. Now we'll go to Ken Kramer from Spaceflight Now. Ken?
Hi, thank you. Congratulations again on a fantastic mission. 2 quick questions. First, for Mike, I wonder if you could compare the relative amount of water and carbon dioxide in all the comets that we have investigated, the 5 so far. And a question for everyone, did you expect to see these particles? And I wonder if the cameras were retargeted to try to catch those pictures. Thanks.
I think this comet probably has more CO2, more dry ice than any one that's been measured. However, much of the information I have on the other measurements is unpublished measurements by our Japanese colleagues using the Akari spacecraft, so I'd rather not talk about that in any detail because they haven't published their results yet. We did not expect these particles. As I said at the beginning, the fact that we had this experience in Temple 1 of excavating material and not seeing the particles led us to not really be thinking about them when we got to this comet, even though theoreticians have drawn lots of cartoons showing this kind of phenomenon. They were completely out of our point of view because of the experience at Comet Temple 1.
And we'll go to the call from Emily Locke-Dawala from Planetary Society. Emily?
Hi, this one's for Jessica. I know that I think that there were some albedo variations, or maybe even some color variations on the surface. I'm wondering if you're seeing that in your data. If you've gotten anything from your spectroscopy on the composition of the surface yet.
There are albedo variations. You can see them in the initial images we released, but we have not yet had a chance to look at the surface in any detail. It's a much more complicated problem than the coma because of the background. It's physically complicated, and it's a little more complicated for our instrument. And we've been focused on this ice story, to be perfectly honest, and that's next for sure. So again, I have to say stay tuned. Sorry about that.
Okay, I think that's going to do it for the questions. I have a couple of comments. First of all, on September 10th, there was an incredible symposium, Comet Discoveries and Encounters, held at the museum here in Washington, where some of the folks here on the stage participated in. I'd like to tell our television audience that you can go to the NASA YouTube site and also solarsystem.nasa.gov, and you can take a comparison from September 10th that was said about comets to now, and you can go in a little deeper, more context. And actually, I was wrapping this up, but now we have another question. Someone said, no, I want to talk. So, can we have the name again, please? Phil Play, go ahead, from astronomer. Go ahead, Phil.
For any of the 3 who can answer this, I may have missed it, but the comet is a peanut shape with 2 lobes and a smooth core connecting them. And you say water vapor is coming from the connector while more carbon dioxide is coming from the lobes. Why would that be? What is it about the structure of the comet that we're seeing that differentiation of the material ejected?
Well, I don't think we know yet. There's a couple of big picture ideas. One is that material is being redistributed over the comet. So you have dust, and in particular, coming out with the CO2, it gets redeposited in the low and gravity low in the middle. That creates a smooth dust covering. Now that's going to affect how the sunlight is able to reach the bottom, the interior of, not the bottom, but the interior of the nucleus. And so it's possible that that middle either just doesn't have any CO2 and it has been used up, or it never did, or it's also possible that the dust coating is preventing the sunlight from reaching the CO2 that's actually in the middle. So if we did another impact experiment, we could tell the difference. Told you I'd get back to it, Pete.
Okay, what I'm going to do here is I'm going to pause a little bit because we have reporters joining, and we may get some latecomers again. But before we do that, I want to turn it over to Jim Green. I think you have some comments, sir. Go ahead.
Yeah, I just have a question I'd like to know. And now that you're seeing the material leaving and perhaps can get an estimate of its mass, perhaps you can tell us, is this comet sublimating and expelling gas faster than the others, and perhaps what's its future life? Is it in the last stages of its life? Will we see it again in 6 years when it comes around, or what?
Okay, I will attempt to answer that. Some parts of it. It is certainly producing more total water vapor per second than Comet Tempel 1, even though Comet Tempel 1 is much bigger. It's roughly 300 tons per second. I think that roughly at least half, and maybe 2/3 of that, is coming from the chunks of ice that come out and then gradually sublime. And only something like 1/3 of it is coming directly from the nucleus, probably mostly near the waist. And that says it's a very active comet for its size. If you try to integrate how much mass is lost as it goes through perihelion, the comet should be losing, on average over the entire surface, something like a meter of surface material every perihelion passage. So at the waist, there's maybe 100 perihelion passages left. So it'll be gone in that length of time.
Jim, did you have a follow-up?
No, it just sounds like in 6 years when it comes around, we'll be able to see it again.
Yep.
Okay, thanks, Jim. Okay, let's try this again. Any other questions before I wrap it up? Going once, going twice? Okay, again, ladies and gentlemen, on the TV audience, September 10th, symposium, go to solarSystem.nasa.gov, compare what you heard about comets then at that event to now, deep comparison, deep context. Always go to www.nasa.gov for all of NASA's missions, and of course for EPOXI, nasa.gov/epoxy. And as I say it once, and I'll say it 1,000 times because it is absolutely true, science never sleeps. Thank you all.